Okay, guys, we're going to talk about multi-compartmental models. We're going to be kind of going full circle, coming back to what Dr. Basu was covering earlier in the semester and talking about. He was only talking about one compartment models, which is usually what we use when we're talking about pharmacokinetics, but we will see that it's almost always oversimplifying things. Up until now, we've used one compartment to describe what's happening with our drugs, and what we look at is, here's before we've administered a drug. If we then administer a drug, one compartment means the drug distributes evenly everywhere in the body all right away. So that's one compartment. So the drug comes in at rate KO or RO or dose rate or whatever you want to call it. The drug comes in. It distributes into one volume of distribution, and then it's eliminated. It's a very simple model. It's a one compartment model, and this is what relates to if we plot natural log concentration versus time, and we give an IV bolus like this. Says we're going to get a C0 or Cmax here, and it's going to be instantaneous, and then we're going to have a log linear decline that will follow that concentration any time t along this line will equal to our initial concentration C0. Let me change the color here because we can't really see that, can we? Ct is going to be equal to C0, this concentration here, times e to the negative k, which is the slope of this line, times the time difference between these two concentrations that we want to know. Okay? You guys should all be very familiar with that equation. I call it peanut butter because you got to know it like peanut butter and jelly. This is peanut butter. We got to know it inside and out. So that's a one compartment model, which is what we've been using thus far to describe kinetics, and usually is just fine. Because once we get into two compartments, as you'll see, things get mighty messy, and sometimes we have actually maybe many more compartments than just two. With a two compartment model, which is probably more accurate for most drugs, we have the drug is given, and initially the drug distributes into the bloodstream and these highly perfused organs, right? So the liver, the lungs, the heart, right? And the kidneys probably should be in there. Maybe you can't see them. So we have our initial distribution, which is our first compartment, or compartment number one here. And then eventually the drug will distribute out into other tissues of the body. So the drug comes into compartment one, into the bloodstream, and then it moves at a rate K12, so it's moving from compartment 1 to compartment 2, which is the other tissues in the body. And then it also needs to move back from compartment 2 to compartment 1, so this is K21, back into the first compartment, which is the bloodstream and those highly perfused organs, and that's where it has to be to go out of the body, right? Because that's where it has to be to get to the liver and kidneys, to get out of the body. So this is probably more indicative of what actually happens, which means there's two compartments, not just one. And in fact, there could be other compartments here. There could be in a compartment off of there. It could get very complex. But we're going to only talk about really two compartment models this week. So what does it look like when you actually plot this? As we said, with a one compartment model that we're seeing here, here's one compartment. If we give a drug, let's give it IV bolus because that's the easiest thing to look at, right? We give it, we have our y-intercept, this is log, you can see this is a log scale. we can see we have a log linear decline with the slope of it being k, whether you want to call it ke or kd, whatever you want to call it. It's the elimination curve, slope I should say, and it's just rise over run there, right? You know how to figure out your k. So the concentration at any time t along here can be determined if you know one concentration that's going to be C0, or the larger concentration has to be C1. CT has to happen after C1 or C0, whatever you want to call it, times e to the negative KT. E to the negative KT represents the fraction of drug that's remaining at time t, right? So that's what e to the negative KT stands for, and that's just our first compartment. So the K is the slope of that line. T is the difference in time between the two concentrations that we're talking about. So we can find any piece of that as long as we have the other pieces, right, algebraically. Now a two-compartment model is when we plot, so you can see we've still plotted this on a log linear line, so log concentration times versus time. What we can see is this is not a straight line. If this is not a straight line, then there's greater than one compartment. See how this is a straight line and we have an elimination rate constant, which is a slope there? If we plot our log concentration, just like it is here, versus time, and it's a curved line, then we know that we have more than one compartment. That's how we can tell. Here, this week, what we're actually able to do is be able to figure out this actually is one compartment, but you can see that if we extrapolate the line back here, that it doesn't describe this part of the curve, which is actually your distribution phase. That movement into that first compartment is the distribution phase, and then this is the slow phase. So what we do is we actually subtract out. We're going to talk about stripping in a minute. We figure out what the slope of this line is and the y-intercept of this line, and this is our slowest compartment. So the slope of this line goes here, because this is our slower compartment, our second compartment. So the slope of this line is K2, and that belongs there. The y-intercept for that second compartment is there, and so that is that number there. Actually, it's got to be the, not the log, but you have to take the anti-log of whatever that number is so that you can get the actual number. Okay, and then what we do is we subtract out what's remaining and we plot that, which is what this is here. And so here we have a different slope. It's a faster slope, isn't it? So this slope belongs here in K1, and the y-intercept, which you can't see at all because I've scribbled so much, but the y-intercept here belongs to C1. And so we actually have two lines here described, and these two lines represent the fast compartment and the slow compartment. If you add those together, you'll get, as we have here, you'll get what our actual two-compartment model looks like. And you still can determine any concentration at time t if you add the first compartment and the second compartment together. If you had a third compartment, you would have C3e to the negative K3t. This is important. This is what we're going to be working on with our workshop. Let me just do one more thing here, because I think... So what you do here is you have your concentration, your natural log concentration time. If you have one compartment, your elimination curve is going to be K. Here's going to be your y-intercept, right? So your concentration at any time t will be your y-intercept times e to the negative kt. Pretty simple, right? if we plot, oops, I didn't really mean to do that, but oh well, that's okay. If we plot a natural log concentration time and it looks like this, then we know automatically we have more than one compartment, right? And we can then say, well, this is a straight line, so this represents our slow compartment. I should do this in a different color. This represents our slow compartment. So the slope of that line and the y-intercept of that line represents our second compartment. So C2 e to the negative K2 t. So this needs to be the C, not the LNC, but so this number would be the LNC, so you'd have to take the anti-log to get that. And then you look at what's left, and you might have something like this that's left with a steeper slope. It's going to have a steeper slope because it's a faster compartment, and it's going to have its own y-intercept, isn't it? So we're going to add that together, and that will give us our total concentration at any time t will be these. Here's the first compartment, and here's our second compartment. Okay? So these are called model dependent parameters. Whoopsie. The reason for that is it depends on the model in order to be able to determine them. So model dependent parameters are our macro constants. Macro constants are what we just did. Our y-intercepts, C1, C2. These are the y-intercepts, right? And our slopes, which are K1, K2, which represent the slopes of each of those compartments. These you have to know how many compartments there are in order to be able to determine those, don't you? So these are called macro constants. Micro constants are the movements between the compartments. So we have compartment 1 and compartment 2. Compartment 1 is where the drug comes in and the drug goes out. So this is drug coming in, and then we know that drug will move from the first compartment to the second compartment. That movement is going to be at the rate of K1 to 2, so we call it K12. That'll go between from the first compartment to the second compartment, and then the movement of the drug from the second compartment back to the first compartment is called K21 because we're moving from 2 to 1. Okay, so these are both called micro constants. So K12, K21, and then K1 out of the body is called K10. That's our drug how quickly our drug is being eliminated from that first compartment. These are all called micro constants. These are all dependent upon what model you're using. You can't determine any of these without knowing what the model is. Okay, we're going to stop there, and I'll see you in the next video.